In this lecture, I'm going to be returning to atoms for a few minutes. We're trying to build up to understanding emission and absorption line spectra. We've covered continuous spectra now, and now we want to look at how emission and absorption lines come into spectra. To understand this, we need to understand in pretty serious detail the way atoms and light interact. And so we need to know a little bit more about atoms, and then in the next lecture I'll talk about how they interact. And then finally we will build that up to how that gives us the characteristics of emission and absorption line spectra. So coming back to atoms, here's our carbon atom that we talked about a couple of lectures ago. We had the nucleus with its protons and its neutrons, and we had electrons in these different levels on the outside that we talked about as the electron shells. And just reviewing what we said then, the electrons can only have certain amounts of energy. So these electrons have a different amount of energy than these electrons, and there can't be anything in the middle. The carbon atom only allows energy of this much or energy of this much, not anything else. And so the amounts of energy that we have depend on what element it is. So hydrogen has a completely different set of energies than carbon, and also on whether the atom is ionized. So if we took away one of these electrons, so that there were only 5 of them, the actual energy levels would change. We would have a different set for that new ion of carbon. And hopefully we remember that these different levels are called energy levels because they reflect a different amount of energy. I'm going to talk a little bit more about the energy levels for hydrogen now, because hydrogen is the most important element in space. 95% of what we see in space is hydrogen. So we need to really understand hydrogen, and conveniently it's also the easiest element to understand. Sort of got a drawing of a hydrogen atom over here. Its nucleus is down in the center, and in typical hydrogen there's only the one proton, there are no neutrons, and then we have the one electron, which I haven't drawn in here. We just have the energy levels. Now, I want to talk about the names of these levels, and also we now want to know how much energy does each of these levels have. I've sort of taken the picture and straightened it out a bit down here, sort of made the energy levels look a little bit more like a ladder over here, but this is illustrating the same levels that you see here. The way I've drawn it here, you see that the levels are getting closer and closer together. That is completely realistic. The energy levels do get closer. I have labeled the first 4 of them, then there's a couple more, then there's one that I labeled as n equals infinity. There really are infinitely many levels in between here and here, but at a certain point we might as well just call it infinity because all of the energies are going to end up being pretty much the same at that point. The lowest level, which has the least amount of energy, is always going to be called the ground state, regardless of what atom it is. The lowest level is going to be called the ground state. So my lowest level is called the ground state. And we just sort of number these things, 1, 2, 3, 4. So the ground state is always going to be n equals 1. And we're going to say that the ground state is actually going to have 0 energy. That's not really true. There is energy in that level, but we're going to call it 0 and define everything else based on that. The other levels are called excited states. They're excited because they have more energy, so the electron is more energetic, it's excited, kind of metaphoric use there. So these are excited states. The first one up from the ground state is called the first excited state. The next one is the second excited state, and so on. You'll notice that when I number the levels, the ground state is n equals 1, and it's just the number we use to count the levels. And the ground state is the first one, so it's n equals 1. The first excited state is n equals 2. So you got to be careful when you're reading a problem. If it asks about the first excited state, in that case, n equals 2. So 2 goes with first, 3 goes with second, and so on. It's kind of tricky to remember that. And there is a formula for the energies of these higher levels, and that is given by this formula right here. Energy is equal to 13.6 times the quantity of 1 minus 1 over n squared. N is just the number of the level over here. You can easily see that if n equals 1 for the ground state, then this is 1 minus 1, so 0. So 13.6 times 0 is 0. The ground state is going to have an energy of 0. And we can figure out these other ones using the formula. The 13.6 only applies to hydrogen. If there is any other element, this number doesn't apply anymore. And that number will change. So I'm giving you this formula because the ones we're going to do math with are always going to be hydrogen. You do not use the 13.6 for any other element. The 13.6 is relevant because if you have done some advanced math, you can imagine putting infinity in here for n. 1 over infinity is 0, so 13.6 times 1 minus 0 is 13.6. The ionization level, this n equals infinity, has an energy of 13.6 for hydrogen. And if the electron gets more than 13.6 electron volts of energy, that's the same units we used when we were dealing with energy of photons, if it gets more than 13.6 electron volts of energy, then the electron leaves the atom altogether and we get an ion of hydrogen instead of neutral hydrogen. So again, the 13.6 comes from the fact that that's how much energy it requires to take the electron and make it leave the atom completely to cause ionization. And that's going to be different for every atom because you have a different amount of charge in the nucleus. So, but all hydrogen uses the 13.6. So we would probably like to know what the energies for these other levels are, like the first, second, and third excited states. You're going to be using these numbers over and over again in your homework problems. You may want to refer back to this. There's also places in the book, figures where it shows this, things like that. We're going to figure out the first and second excited states now, and then you can do the third state for your homework just to practice for yourself. So for the first excited state, n equals 2. So my formula for hydrogen, because this is hydrogen, 13.6 times 1 minus 1 over n squared, it's going to become 13.6 times 1 minus 1 over 2 squared. That's 13.6 times 1 minus 1/4. And we can quickly figure that out. And we get 10.2. This is in electron volts. The first excited state has an energy of 10.2. Again, the ground state was 0. And the ionization level, the energy was 13.6. So 10.2 being in the middle is a good thing to recognize, or that's a good check. For the second excited state, n equals 3. So I'm going to do 13.6 times 1 minus 1 over 3 squared. So that's 13.6 times 1 minus 1/9. You get 13.6 times 8/9. Which is about 12.1. I would encourage you at this point to just go on and do the rest of this problem, which is part of your homework. Go ahead and do the third excited state and make this little diagram someplace. This will be a useful thing to refer to. It'll save you some time on your future problems.